In this video presentation, I'll be discussing the electromagnetic qualities of inductive heating. The topics of this video are the basics of inductive heating, the magnetic flux density inside of a solenoid, and the magnetic flux linkage and inductance of a solenoid. These topics should provide a brief overview on the electromagnetic qualities of a solenoid inductor and how it may heat up certain materials. When an electrical current flows through a conductor, it creates a magnetic field. The direction of the magnetic field may be acquired using the right hand rule. If you point your thumb in the direction of the electrical current flow, the direction of the curl of your fingers point in the same direction of the magnetic field. Therefore, if you alternate the direction of the electrical current, it will create an alternating magnetic field. This alternating magnetic field creates localized electrical currents within the conductive material called eddy currents. These eddy currents flow against the resistance of the conductive material, causing the conductive material to heat up. This is called Joule heating, which is what generates most of the heat in inductive heating. Inductive heating is most efficient through a solenoid because the magnetic flux is concentrated within the coil, which provides the maximum heating rate. As you can see, the magnetic field still flows in relation to the direction of current flow, but in this case, the magnetic field travels to the inside of the coil. From the equation, we may acknowledge that the magnetic flux density shares a negative relationship with the length of the solenoid, but shares a positive relationship with the amount of current flowing through the solenoid and the number of turns used to wind the conductor into the shape of the solenoid. Therefore, it is clear that a short, tightly wound solenoid would have a greater magnetic flux density than a long, loosely wound solenoid. The direction of the magnetic flux density may also be derived using the right-hand rule, which is denoted by Z hat. Overall, the efficiency of the inductive heating depends on the strength of the magnetic flux density, which is dependent on factors such as the length, number of turns, and current of the solenoid. Once the magnetic flux density is acquired, we may use it to calculate the magnetic flux linkage through a loop using the equation denoted by phi. This basically takes the magnetic flux density and the area of the solenoid to compute the magnetic flux linkage through one loop. The total magnetic flux linkage may be calculated by multiplying the number of turns in the solenoid by the magnetic flux linkage through one loop. Using this value, you may calculate the inductance of the solenoid by dividing the total magnetic flux linkage by the current flowing through the solenoid. Overall, the inductance of the solenoid shares a positive relationship with the efficiency of the inductive heating process due to its reliance on the magnetic field intensity and the amount of current flowing through the solenoid.